Well, dear students, in our last class, we started solving numericals on the chapter Electric Potential and Capacitance. If you remember, we have solved some 7 numericals in the last class, and we'll continue with the numericals in today's session also. I hope that all of you are having textbooks with you, and you should go through the questions and then refer the solution for each question being discussed here. Understand? Now accordingly, let us refer next question number 8 from the text. So here is page number 87 on the chapter Electric Potential and Capacitance. Question number 8 is, in a parallel plate capacitor with air between the plates, each plate has an area given 16 10 power minus 3 square meter and the distance between the plates is given 3 millimeter. Calculate the capacitance of the capacitor. If this capacitor is connected to a 100 volt supply, what is the charge on each plate? Well students, for question number 8, you refer, given that area of each plate 6 into 10 power minus 3 square meter, remember, and distance between the plates 3 millimeter, and it is connected to a battery of voltage given 100 volt. This is what given. What you are asked to find? You are asked to find the capacitance of a parallel plate capacitor. This is what the arrangement: positive charged plate, negative charged plate. You know the mechanism also you know. Well, now for this capacitor, C is equal to E naught into A by D is the formula, because it is said the space is filled with air between the plates of the capacitor, hence E naught A by D. Substituting the values, students, you know the value of E naught 8.854 into 10 to the power minus 12, area given 6 in 10 power minus 3, distance given 3 into 10 to the power minus 3 millimeter. So that this and this cancel, 3 once, 3 twice, 2 into this number, 2 4 ja 8, 2 5 ja 10, 2 8 ja 16 plus 1 17, 2 8 ja 16 plus 1 17, and decimal points positions here into 10 to the power minus 12 farad. This is the capacitance of the given parallel plate capacitor. It is basically uncharged, and when kept connected to the battery, it gets a charge. Accordingly, what is the charge on each plate? Charge on each plate of the capacitor. Charge on each plate of the capacitor. Charge on each plate of the capacitor. That is, Q is equal to C into V is the formula for charge on each plate of the capacitor. C into V. Each plate has area A. D is the distance between the plates, and the charge on each plate. One plate has positive charge, the second plate is equally negatively charged. So capacitance is found here 18.854, sorry, 17.708 into 10 to the power minus 12 into voltage. The battery supplies voltage 100 volt, which is 100 means 10 power 2. This comes out to be 17.708 into 10 to the power minus 10 coulomb. Observe the steps, students. This is a very simple question asking you to find the capacitance whose dimensions are given. Area given, distance between the plates given, and ask you to find capacitance. And when such a capacitor is connected to a battery which supplies 100 volt, then what is the charge on each plate? This is a simple and easy question. Well, students, now question number 9. Question number 9. What is question number 9? Explain what would happen if in the capacitor given in exercise 2.8, a 3 millimeter thick mica sheet of dielectric constant 6 were inserted between the plates, when while the voltage supply remains connected after the supply was disconnected. Look at this question. The same capacitor, remember students, the same capacitor, when battery is kept connected, a dielectric medium is placed. And the same capacitor to which when battery is disconnected and dielectric slab is placed. How about the answers to the question, what happens to the capacitance and the charge they are asking for? Look at the arrangement. Take the capacitor. Well, students, this is battery kept connected, battery disconnected. Here is the arrangement shown. Battery kept connected, battery disconnected. Battery connected, battery disconnected. Now, when battery connected, battery disconnected, while voltage supply remains connected, this is voltage supply. This is for question A, this is for question B. Look at the arrangement drawn according to the two questions. While the voltage supply remains connected, after the supply was disconnected, connected. So here connection shown, here disconnection shown. You observe carefully, no connection. Now under this situation, what would happen? For the charge we calculated, for the capacitance we calculated in the earlier question. Yes. This is under the situation that a dielectric constant K is placed here. Here also dielectric constant K is placed. Dielectric constant K is filled with battery being connected, with the battery being disconnected. Voltage supplied, voltage is not supplied. Now remember, in this case, whether you connect the battery or disconnect, what is the capacitance? C dash will be equal to Kc. Remember. And what about voltage? Voltage V dash is equal to V only. Why? Because though capacitance increases, but voltage decreases. However, because of the presence of battery, the decreased voltage is made up, is balanced due to the supply of voltages by the battery. Hence, in this regard, if you calculate Q dash, it will be new capacitance into new voltage. This comes out to be, remember students, C dash is Kc into V dash is V. And remember, this is Q dash is equal to K into, what is C into V? Original charge. Therefore, new capacitance is K K times original capacitance, and new charge is K times original charge. This is the result when battery is kept connected. Remember, whenever battery is connected, the capacitance will increase K times on inserting the slab. Which slab? Dielectric slab. And what about voltage? Will remain same. Why? Because though capacitance increases, voltage decreases, and decreased voltage is balanced, is made up by the presence of battery, which supplies charges to bring the voltage back. So accordingly, now what is the new charge? New charge is new capacitance into new voltage. New capacitance is K times C into voltage V, same, therefore Q dash is Q. So accordingly, our answer becomes, what is the capacitance in earlier part? 17.708 in 10 power minus 12 farad, to which you should multiply with the K. What is K given in the question? Dielectric constant is given to be 6. Therefore, your answer is 6 times this capacitance for the sub part A. Similarly, what is the charge? Here is the original charge calculated. Now, after inserting the dielectric slab, the new charge is K times, that is 6 times this charge. You have to answer. I hope you understand. Refer carefully. This is for first question A. Look at the first question A. Voltage supply remains connected. Battery remains connected. Capacitance K times. Battery remains connected and dielectric slab introduced. What happens to capacitance? Becomes K times. What happens to charge? Becomes K times the initial charge calculated in question number 8. And remember, the slab is completely filled between the plates of the capacitor. Therefore, capacitance becomes K times. If it is partially filled, then they would have mentioned how much space it occupies. Then it is a different answer. And at the simultaneously, let us also refer answer to the question B, sub question B, where voltage supply was disconnected said. So, voltage supply was disconnected, I write here. Observe students carefully. Now, in this case also, capacitance is K times only, because capacitance, the ability to collect the charges, has nothing to do with the battery being connected or disconnected. It depends only on the dimensions and of course the space being filled between the plates. What space it occupies, what matter it occupies. Our capacitance purely depends on dimensions, does not depends on how much voltage you are supplying. How much voltage you are supplying, it doesn't matter. It depends on dimensions and of course the surrounding medium, hence K times. What about voltage? Voltage will become, remember, V dash is V by K, remember, because battery is disconnected, therefore this time voltage decreases, like force decreases to 1 by K times, voltage decreases to 1 by K times, even electric field decreases to 1 by K times. All this we referred in our earlier discussions, if you remember carefully. So here also voltage decreases because capacitance is though increased, but to bring the voltage back there is no supply. If there is a supply, then voltage would have brought back, like in part A. In part B there is no source to bring the voltage back to its original because it is disconnected. Hence its voltage will decrease to 1 by K times. This is the important difference you can note down. This is the important difference you can note down when battery is being connected and being disconnected, students. Hagadre, now what about charge? Charge will be Q dash is equal to new capacitance into new voltage. What is new capacitance? K times C. What is new voltage? V by K. And you can now judge what is the answer very easily. What is that? K and K cancels, students. You are left with the Q dash is equal to what? C into V. What is C into V? Q. Therefore, in this case, Q dash is Q only. Means whatever the charges present on the plates will be there. Because battery is disconnected, no more increase in charge. Therefore, Q dash is equal to what? Q only. ಅಂದರೆ ಫಾರ್ ದ ಸೆಕೆಂಡ್ ಪಾರ್ಟ್ ದಿಸ್ ಈಸ್ ದ ಸೇಮ್ ಚಾರ್ಜ್. ಫಾರ್ ಫಸ್ಟ್ part, charge is k times this charge. However, whether you keep the battery connected or disconnected, capacitance will always increase to how many times, students? K times. The capacitance will increase to k times, whereas the charge will be k times if battery is connected and will remain same as original if battery is disconnected. In the process, to know the charge, we should know voltage, because amount of charge mainly depends on the capacitance of the conductor and the level, that is voltage level. Hence, so I have not numerically calculated answers, students, remember. So just shown k times, and what is the value of k? 6. Therefore 6 into this value, as in question number 8. You refer question number 9 carefully, because in question number 9 they asked you to what are the changes in the answers made in question number 8. What answers we made? 2 answers, capacitance and charge. What about them according to the situation given in question number 9? Yes. So in the process we referred what is voltage. Hence charge as well as capacitance becomes k times. What is k? Dielectric constant, which is given to be 6. The value 6, which is dimensionless in question number 9. When battery disconnected, remember, disconnected, capacitance will be k times, but charge will be q only, same as what? Well, students, here we can also notice the one important parameter. So in addition to capacitance, voltage and charge, we can also note down how about the variation in the energy stored in the capacitor in this case as well as in this case. We know the general formula for energy stored in a capacitor, like half CV square. Of course there are 2 other forms. So we can refer how about energy variation when battery being connected and when battery being disconnected. We can also refer that part. Okay, and even you can also note down how about electric field between the plates of the capacitor, because you know very well between the plates of the capacitor there is a uniform electric field is being existing. And how about electric field varies when battery connected, how about electric field varies when battery being disconnected. The variations of electric field will be similar to that of variations in potential. Okay, so I also write here further points, I write here, you just refer them very importantly, remember. So battery connected, battery disconnected, remember. So further, so 3 parameters we referred, students, in the question. As for the question, we referred 3 parameters. I would like to suggest you other parameters also, like what about electric field? Will be same as its original electric field. There is no change in the electric field because potential is balanced, electric field is also balanced. What about electric field when battery is disconnected? It will reduce to 1 by k times. If there is a battery, electric field is make up. When there is no battery, electric field will reduce to 1 by k times. And what about energy? U dash is of C dash into V dash square, and we will refer what is C dash when battery connected, what is V dash when battery connected. Okay, U dash is equal to, remember, new energy of into C dash Kc into what is V dash? V only square. Look at this, continuing with few more terms. This is one important parameter. Now referring this parameter, this becomes U dash is equal to K into of CV square. Therefore U dash is equal to K times U. What is U? original capacitance. Energy of original capacitance, that much energy it can sustain. When you design a capacitor, it has a certain capacitance charged to certain potential, and a dielectric slab when placed, remember, for such a capacitor dielectric slab is placed, energy will also become k times original energy. Without dielectric slab, with dielectric slab. Without dielectric slab, energy U is equal to half CV square. Without dielectric slab. And battery being connected, and if you insert dielectric slab, energy becomes k times. Understand carefully. A capacitor is designed, charged to certain potential, battery is being kept to keep the potential constant, and in such a situation, if you fill the space between the plates with a dielectric slab, then energy becomes k times. How about energy when battery is removed? Battery is disconnected and the slab is placed. Battery is removed and the slab is placed. Battery is removed and dielectric slab is placed. So U dash is equal to half into C dash into V dash square. Half into C dash is Kc. And what is V dash? In battery is disconnected, V by K. So V square by K square. So you will be left with half into CV square divided by K. And what will be this? This is U, original U by K. Means, students, when battery is disconnected, energy will reduce to 1 by K times. When battery is kept connected, energy will become K times. Remember, all these changes are due to inserting dielectric slab. All these changes are due to inserting dielectric slab. Well, students, in the question number 9, you were asked to see the changes calculated in question number 8, like capacitance and charge, when battery being connected and disconnected and dielectric slab is placed. Further, we are discussing how about variation in electric field, how about variation in energy in both cases. We are adding few more quantities and their changes under the same situation. You understand this carefully. Battery connected and disconnected, but slab will remain there, dielectric slab will remain there. Generally, all the formulas what we discussed with air is the space. Instead of air, if there is a dielectric medium, then how about changes? That too, when battery connected and disconnected, it makes difference. There is a difference, battery being connected and disconnected. Observe all the steps written very carefully. This is additional information. Remember, students, additional information extending the idea of question discussed in question number 9, where we are asked to look at the changes in capacitance and the charge. So in the process, we also extended our idea for electric field, energy and all that. Well, students, now refer question number 10. A 12 picofarad capacitor is connected to a 50 volt battery. How much electrostatic energy is stored in the capacitor? 12 picofarad capacitor and 50 volt battery. A capacitor being connected to a battery. This is 50 volt battery. This is a 12 picofarad capacitor. What is the energy stored? Capacitance given, voltage given. Therefore, energy stored. Electrostatic energy stored. This is simplest question, students. Electrostatic energy stored. This is direct and simplest question, students. U is equal to half CV square, you refer, which is half into C is 12 into, pico stands for 10 power minus 12, 50 whole square. This is 2 1 times, 2 6 times, 6 in 10 power minus 12 into 50 square, 2500, 5 square 25, 10 square 100. This is 25 into 6, 150 into 10 to the power minus 10. 25 6 times is 150, 2 zeros, 10 power plus 2. The here minus 12, 10 power minus 2. R, this is 1.5 into 10 to the power minus 8 joule. Because if I place the decimal point here, 10 power plus 2. This is simplest question, students. You refer the simplest question. So here answer is this, directly half CV square formula with which you can find the answer. You refer all the solutions for each question carefully. Students, I suggest you, please read the question carefully, not once, read minimum 2 times, try to understand and follow the solution. Well, students, if you have followed question number 10 and completed, let us refer question number 11. Question number 11 is of this kind. A 600 picofarad capacitor is charged by a 200 volt supply. It is then disconnected from the supply and is connected to another uncharged 600 picofarad capacitor. How much electrostatic energy is lost in the process? Remember, students, here there is one important discussion. You can consider 2 capacitors in which one is charged and another one is uncharged. When a charged capacitor is kept in contact with uncharged capacitor, so charges will flow from charged to uncharged. So some energy will be lost in the process, and that is what we are asked. To solve this numerical, let us refer the necessary theory, students, for question number 11. Remember the important theory I consider. Let us consider 2 capacitors, C1 and C2. Remember, students, this is important. This is important. 2 capacitors C1 and C2 are given to you. Assume that they are charged to potentials V1 and V2. They are charged to potentials V1 and V2. Charges are given to raise the potential. Students, charges are given to raise the potential, and to give charge, how much ability to collect the charge, that is characterized by its capacitance. So 2 capacitors, assume initially. Let us learn this theory and we will come back to the question. The numerical question to solve, we need to understand some important concept here. Obviously they have charges. Obviously now they have charges Q1 and Q2 respectively. When charged Q1, potential rises. Charged Q2, potential rises to Q2. Now in this case you can write Q1 is equal to C1 V1, and in this case you can write, students, Q2 is equal to C2 V2. Now after this, if they are connected, say in parallel, assume, then they will attain common potential after charge is being transferred from one capacitor to another capacitor. This is well, students, now charges will flow from one capacitor having higher potential to another capacitor having a lower potential. Charge will flow from one capacitor of higher potential to another capacitor of lower potential. How long it will flow? Until both of them do attain a common potential. So they are being connected in this way, hence they will attain a common potential, common PD, and what is that common potential we can also calculate. Remember, initially two capacitors were given separately, individually, their capacitances, charges to rise to the respective potentials, and of course they have some energy U1 and energy U2. Even you can also refer that energy U1, here is energy U2. Yes, this energy, as you know, of C1 V1 square, off into C1 V1 square, students. Here energy is off into C2 V2 square. Energy is also there. Now for this arrangement you can refer, this is the new arrangement being made. This is a new arrangement. The charges will flow from one capacitor of higher potential to another capacitor of lower potential. How long it will flow? Until they attain common potential. Assume that now they have attained a common potential. It is as same like a heat flows from one body at higher temperature to another body at lower temperature. How long it will flow? Until they attain same temperature. That is in a very similar way. There heat flow, here charge flow. Yes. Assume that both have attained a common potential. Common potential, let us say V, common potential. Now to calculate common potential, what is the common potential they have attained? Let us find the third. Using the principle of conservation of charge. Here total charge is Q1, Q2. Here Q1 dash, Q2 dash. Let according to conservation of charge. Charge principle can apply. Total charge before combining, that is Q1 plus Q2. Total charge after combining must be same. However, charges are redistributed. On the capacitor 1, now charge Q1 is not same, it is different. Now after combining like this, the charge on capacitor capacitor C2 is no more Q2, it is different, but sum is the same. Sum of charges before and after would be same. This is equal to Q1 dash plus Q2 dash. I write. What is Q1? C1 V1. Look at this. What is Q2? C2 V2. What is Q1 dash? You can write Q1 dash as C1 into V plus what is Q2 dash? C2 into V. This is important, students. Why? Because whether you combine or without combination, whether with combination or without combination, capacitance of each will not change. However, what is changed? Individual charges are changed. What is changed? Potential is changed. However, both have attained same potential, common potential. Hence, C1 into V, Q1 dash, C2 into V, Q2 dash. What is not changed here? Capacitances are not changed. Why? Because this is well known, very well known that capacitances depends on their dimensions, surrounding medium, but not on amount of charge and potential raised. It does not. Like, again I repeat the example, a water tank of 1000-liter capacity, it depends on the dimensions. If you want to have a tank of 1000-liter, you have certain dimensions, certain measurements, certain area, certain diameter, certain height, is it not? But does not depend how much water. You can fill completely 1000 liter water, it can collect, or you can fill 500 liter water also, it can store. Even you keep it empty also, it remains empty only. Yes, in the same way, capacitance will not alter. So V is the common potential. So what you will find? C1 V1 plus C2 V2 is equal to C1 plus C2 into V. Therefore, V is equal to what? C1 V1 plus C2 V2 divided by C1 plus C2 is the common potential attained. This is important result, friends. I mentioned here. This is a formula for common potential attained. This is important. This is one part, and remember friends, this is the necessary theory we are discussing pertaining to our question, and this discussion will be definitely helpful to answer various other questions in the objective tests. And whenever two capacitors are individually given like this, charged to respective potentials, and when combined like this, what is the common potential they attain? Like this is the common potential. This is as same as what you studied in the first year course, the principle of calorimetry. When a hot body is mixed with a cold body, then both will attain one common temperature, the resultant temperature which we used to calculate. In a very similar way, the common potential they attain. Now remember friends, in this discussion, maybe that one of the capacitor is uncharged initially. One of the capacitor is uncharged. So in that regard, V2 becomes 0, you can put V2 0. So out of 2, at least one must be charged to some potential. So that if this is charged, assume, and if it is uncharged, then you keep uncharged capacitor with a charged capacitor, then you can also calculate that charges will flow from charged one to uncharged one until they attain common potential. In that case, here V2 becomes 0, you have to put. That is also possible. This is even same as the theory of collisions. If you remember friends, in the first year course, the collision theory, if you remember, two particles in which one particle is at rest and another particle moves and collides with the second particle. Then if they attain common velocity, then we can calculate using the principle of conservation of linear momentum. In the same theory also here you can consider. For a collision to take place, at least one particle must be in motion. If two particles are at rest, collision is not possible. At least one particle must be in motion in order to have a collision. It is an event in which motion of one particle is affected due to other. Similarly, potential of one body is affected due to other. This theory for capacitances and their charges and potentials we can consider. Now if you want, you can calculate what is the total energy initially present and what is the final energy. Like in this case, total energy is U1 plus U2 of C1 V1 square plus of C2 V2 square, remember. Now what is the final energy? Of into C1 plus C2, because how the combination is parallel combination, of into C1 plus C2 into what is the common potential? V square, we can also refer. This is how the result also you are going to get. Well students, now in our question, 600 picofarad capacitor is charged by a 200 volt supply. It is then disconnected from supply and is connected to another uncharged 600 picofarad capacitor. How much electrostatic energy is lost in this process? Now, as per the question, this is 600 picofarad capacitor and it is charged to some potential. The second one is uncharged. This is charged, then after disconnecting it's a charged battery, then it is connected to this capacitor. Then how much electrostatic energy is lost? For that you should know common potential. and then calculate. If you know common potential, what is the final energy you can find out, and initial energy, sum of the initial energies you can add out. So now solution, we are going to write. How to write the solution? Remember, 600 picofarad, 200 volt. So U1 I write half into C1 V1 square, which is equal to half into 600 into 10 to the power minus 12. V1 potential 200 volt, 200 whole square this is, remember, 3 times 300 or 3 into 10 to the power minus 10 into 4 into 10 to the power 4. This comes out to be 12 into 10 to the power minus 6 joule, students. 12 into 10 to the power minus 6 joule. And what about U2, students? U2, remember and refer the question. The second capacitor, similar capacitor, but it is initially uncharged. Initially uncharged. Therefore, U2 is 0. Initially being uncharged, U2 is 0. Therefore, total initial energy is U1 plus U2, which is 12 into 10 to the power minus 6 joule only. Understand and refer very carefully. Here is the theory, still you can refer here. So total initial, I am saying initial means before combining them, in which only one capacitor is charged to some potential, that is 200 volt. Therefore, what is the total energy stored in that capacitor? The second one is uncharged in our question. Hence U2 0, no energy stored. Hence, now what is final energy? To know final energy, you should know what is common potential. Okay. Otherwise, directly also you can substitute. Better to refer what find common potential. Common potential. Look at the formula written. Common potential, because first is charged, second is uncharged. So charges will flow from charged to uncharged until they attain common potential formula. Now potential will, and one more thing is the two capacitors are being identical. Definitely potential will divide equally. Yes. So you will get equal division of potential, that is C1 600, of course picofarad, into 200 divided by 600 plus 600, 1200. Picofarad cancels. Picofarad cancels, and you will be left with the unit of what is called volt. I hope you understand. Okay. Therefore, this goes 2 times. This goes 100 times. Therefore, V is equal to 100 volt. As I said, potential will divide equally. Initially, first one has 200 volt. When combined with another uncharged, potential will divide equally. So each one will get 100 volt. Even if you remember the principle of calorimetry, if thermal capacities of two bodies are same, then temperature will attain in between exactly the hot body whose temperature is lowered by some value, and cold body whose temperature will be raised by same value, like that. So 100 volt. Now what is the final energy you can calculate? U final off into C1 plus C2 into V square. This is V. So I continue here, students. U final continued ಯಾವುದು which is continued? Remember question number 11th solution is continued. U final is equal to half into C1 plus C2 into V square, which is equal to half into, what is C1 plus C2? Identical, 600 plus 600, 1200 into 10 to the power minus 12 pico, V 100 common potential square. Observe the calculation. Six into 10 to the power minus 10 and 10 power plus 4, 10 power minus 6. 6 into 10 power minus 6 joule. U final energy. Remember, energy is lost. Whatever the energy stored initially in the first capacitor, in the process of charging the second capacitor, some energy is lost, because final energy is 6 in 10 power minus 6. Look, well students, in today's class we have learnt two important concepts. In the process of solving numericals, we also learnt two important new concepts rather. Like, what is that? So one, for the question number 9, based on question number 9, wherein how would the capacitance, charge, even potential, electric field, energy vary when dielectric slab is introduced between the plates, with the battery being connected and with the battery being disconnected. Well, also we have learnt one more new concept, like two capacitors, if charged to different potentials, when kept connected, I mean we made parallel combination of them, how about the variations in potential, attaining common potential, and how about the loss of energy due to flow of charge from one capacitor to another capacitor, because the charges are supposed to flow through the wires, connecting wires. So while when charges flows through the connecting wires, some energy will be lost in the form of heat preferably. Yes, so hence we have learnt the theory, necessary theory also. This final energy 6 in 10 power minus 6, which means exactly half of the energy is lost. In the form of what? In the form of heat, because the capacitors are being connected by means of connecting wires, and charges will flow through the wires, and in the process of flowing through wires, it is like electric current. Some energy will be lost in the form of heat, preferably in the form of heat the energy is lost. Yes, the question is, how much electrostatic energy is lost in the process? Electrostatic energy lost is equal to U initial minus U final. Electrostatic energy, that is, you can say delta U is equal to U initial minus U final. What is U initial? 12 into 10 power minus 6 minus 6 into 10 power minus 6. This will become 6 into 10 to the power minus 6 joule. This is lost mostly in the form of heat, or maybe other form of electromagnetic radiation. Well students, there is also another simplified formula to to calculate the electrostatic energy lost. Here we have followed the method what is energy initially, total energy initially, and what is total energy finally. Instead, you can have one simplified formula with which you can directly calculate electrostatic energy lost. What is the formula? I mean, direct formula for delta U you can refer. How to calculate that? I think if these points are noticed very carefully, remember the common potential formula C1 V1 plus C2 V2 by C1 plus C2. In our question, V2 is 0, hence well, students, there is a formula wherein directly we refer to calculate the electrostatic energy lost. What is the formula? Delta U is equal to half into C1 C2 divided by C1 plus C2 into V1 minus V2 whole square. This is the formula. In our question, V2 is 0. In our question, V2 is 0. And C1 and C2 are similar in our question, 6 and 5 picofarad. This is a formula. Students, you may get doubt how to get this formula. This is very simple. How to get this formula? I will show you how to get this formula. Before that, let us check and verify whether applying this formula will get the result, what result we have obtained. Let us verify. Remember, this is half into, in our case, C1 and C2 are similar, C square by 2C into V1 minus 0 whole square. One of the C cancel. This becomes C by 4 into V1 square. What is C? 600 into 10 to the power minus 12 divided by 4 into V1. Initially it's 200 volt. 200 whole square. This on simplification, remember, this is 6 into 10 to the power minus 10 divided by 4 into 4 into 10 to the power 4. 2 square 4, 10 square whole square, 10 power 4. This is delta U. This is delta U is equal to 4 and 4 cancel, students. Now you are left with what? This is answer. Same answer. This is electrostatic energy. Directly you can use this formula in our question. Without referring that formula, you have to make use while answering objective type of questions. With one formula, direct answer. In our question, second capacitor is uncharged, therefore its potential 0. And both are being identical, C into C, C square, C plus C, 2C. Same answer. Now, students, if you have doubt, sir, how to arrive at this formula? How you wrote this formula directly? This is very simple, students. Consider that initially you are given 2 capacitors. Both are being charged to some potentials. Combine the total energy, U1 plus U2, and final energy. After attaining component potential, then take the difference. And work out. Mathematically work out, you will reach this formula. If you want, I will show you the same in brief. Well students, you remember we are referring to question number 11, and in which before we answer that question, before we answering, so we have referred some necessary theory. What is the theory or what is the idea? I repeat once, whenever you are given two capacitors, if they are charged to different potentials and if then they are combined, connected, then charges will flow from one capacitor of higher potential to another capacitor of lower potential. How long? Until they attain same potential, what is called common potential. Yes, in the process of flow of charge from one capacitor of higher potential to another capacitor of lower potential, some energy will be lost, preferably in the form of heat or other electromagnetic radiations. So how much energy is lost is the idea. Here other possibility is, you might have given one capacitor charged to some potential, you are given with another capacitor which is uncharged, now you can connect the charged capacitor to the uncharged capacitor, so that uncharged capacitor has a zero potential initially. So now when it is connected to charged capacitor, it has certain potential initially. Now also charges will flow from charged capacitor to uncharged capacitor, so that the potential of charged capacitor will decrease and the potential of uncharged capacitor will increase. So they will attain one common potential. And what is the common potential, and in the process also how much energy is lost. This is the idea, students, and this question is based on that idea. And to solve this question, we also referred the necessary theory. Now energy lost in the process can also be directly calculated using this formula, as I said. And you may have doubt in your mind how to get this formula. Just I brief out here. Remember, total initial energy of into C1 V1 square plus of into C2 V2 square. Right? Considering that two capacitors both are charged. However, there is another possible case is one is charged and one is uncharged. In that case, second part will be 0. Remember students, this idea is same as like in the collision process. One particle is at rest, say second particle. First particle moves and collides with the second particle. They exchange momentum, they exchange energy. Same. Or the other example I can quote, that is principle of calorimetry. When a hot body, say hot water at say some 80 degrees Celsius mixed with a normal water, say at 30 degrees Celsius, then temperature of hot water will decrease, temperature of cold water will increase, and after some time both will attain one common temperature, resultant temperature. That is, it is not necessary that both should be of same nature of bodies. Different bodies also you can combine, where according to the thermal capacities temperature will vary. Well, coming to this part here, now assume that individually they are charged to some potential. Now they are going to be connected. Now find energy, how to calculate? U final of into, as I shown earlier, they were kept in parallel combination, therefore total capacitance will be C1 plus C2 and they will attain common potential V square. Now what we should do? You know the formula for V. V is common potential. V is nothing but common potential they attain. And you know what is the formula for V? C1 V1 plus C2 V2 divided by C1 plus C2. You have to substitute this there. Now we can calculate energy lost, electrostatic energy lost. U initial minus U final. This is of into C1 V1 square plus of into C2 V2 square minus of into C1 plus C2 into V. V is here. C1 V1 plus C2 V2 divided by C1 plus C2 whole square. Well friends, if you work out this mathematically, and you will be arriving at the same result. This will be the result you are going to get if you simplify. C1 plus C2, the denominator square is there. One of which will cancel, and off you can take common, and LCM is C1 plus C2, and keep simplifying students. You will reach this result. You try this one. You complete the remaining part, work out remaining part, and check whether you will be arriving at this result. Surely you will arrive at this result. Hope you understand this pattern, students. Hope you understand this. Well students, in today's class we have learnt two important concepts. In the process of solving numericals, we also learnt two important new concepts rather. Right? So what is that? So one, for the question number 9, based on question number 9, wherein how would the capacitance, charge, even potential, electric field, energy vary when dielectric slab is introduced between the plates with the battery being connected and with the battery being disconnected. Well, also we have learnt one more new concept, like two capacitors, if charged to different potentials, when kept connected, I mean we made a parallel combination of them, how about the variations in potential, attaining common potential, and how about the loss of energy due to flow of charge from one capacitor to another capacitor. Because the charges are supposed to flow through the wires, connecting wires. So while when charges flows through the connecting wires, some energy will be lost in the form of heat preferably. Yes. So hence we have learnt the theory, necessary theory also simultaneously while solving numerical questions. Well, we conclude this session and we'll continue with the other numericals from question number 12. Yes. Thank you.